Have you ever watched a robot move with incredible precision and wondered, what's really going on under the hood? Well, there's a hidden layer of physics at play, a kind of unseen force. It's called robot dynamics, and it's what turns a lifeless machine into something that can truly move and work in our world. So what exactly is this unseen force? It's not just about giving a robot a destination. It's about figuring out the how. It's really the difference between just pointing to a spot on a map and actually understanding how to start the car, how much gas to give it, and how to steer to get there. To really get this, we gotta look at motion in two totally different ways. On one hand, you've got kinematics. Think of this as just the geometry, right? It's the path. It describes where the robot is and how fast it's going. But the other side of the coin is dynamics, and this is the good stuff. This is the why. It digs into the cause, the actual forces, the muscle behind the movement. And that brings us right to the heart of it all, the pure physics of movement. Because when you boil it all down, every single thing a robot does is just a really, really complex cause and effect physics problem that has to be solved like instantly. Okay, so let's get the official definition on the table. Dynamics is the study of how forces and torques, so pushes and twists, work with the robot's physical body to actually produce motion. It's the literal bridge between a digital command and a physical action. And what's so wild about this is that this incredibly complex field, well, it's all built on something you probably learned in high school science class, Newton's laws of motion. Yeah, that whole force equals mass times acceleration thing, that's the engine driving even the most mind-blowing robots today. But wait a second, if it's just Newton's laws, how hard can it be? Well, this is where the challenge comes in. A robot isn't just one simple object. Every single piece of it has mass. Every joint is fighting against forces. And here's the kicker. When one part moves, it creates a chain reaction that affects every other part. Now toss in real-world stuff like gravity and friction, and suddenly you've got a massive interconnected puzzle on your hands. So how in the world do engineers even start to solve this? Well, they've come up with two really clever methods, and they're basically just two different ways of looking at the very same equation. This really is the million-dollar question in robotics, isn't it? How do you predict what a robot will do? And more importantly, how do you get it to do exactly what you want? The answer lies in these two approaches, forward and inverse dynamics. So let's look at forward dynamics first. The easiest way to think about this is cause to effect. You start with what you know, the forces your motors are putting out. And from there, you predict the motion that's going to result. It's exactly like pushing a toy car across the floor. You know how hard you pushed it, so you try to guess where it's going to end up. And this ability to predict the future, it is absolutely critical for one thing: simulations. I mean, before you go and build a multi-million-dollar machine, you want to be able to test it in a virtual world, right? To see how it's going to react. That's all thanks to forward dynamics. All right, now let's flip the whole problem on its head. This is inverse dynamics. Here, you start with the effect you want. You have a perfect desired path in mind, and you work backward to figure out the exact forces you'll need to make it happen. Honestly, it's what your brain does without you even thinking about it every time you reach for a cup of coffee. It calculates all the tiny muscle forces needed for that one smooth motion. And that is why inverse dynamics is the absolute backbone of real-world robotics. It's the magic that lets a robot on an assembly line lay down a perfect weld every single time, or lets a surgical robot make an incision with pinpoint accuracy. This is all about control. Okay, so we've talked theory, but let's see where this all gets real, because these ideas aren't just stuck in a lab. They're out there solving huge problems every single day, from hospitals right here on Earth to the vacuum of space. And this chart really just says it all. Understanding dynamics isn't optional. It's not a nice to have. It is absolutely fundamental. You want to build a robot that's stable and won't fall over? You need dynamics. You want it to be safe around people? You need dynamics. You want it to be energy efficient? You guessed it. You need dynamics. Just look at medicine. For a surgical robot, dynamics is what makes sure those tiny instruments move with a steadiness that no human hand could ever match. And it calculates the absolute bare minimum force needed to get the job done, which is everything when it comes to keeping patients safe. Or what about our factories? Those massive industrial arms are using dynamics to sling heavy parts around with incredible speed and precision. These calculations are what stop them from overshooting their mark or vibrating all over the place. It's the secret to their speed and reliability. And when we leave our planet, dynamics is what gets us through. It helps a Mars rover figure out how to drive over rocky, alien terrain. It's what allows a robotic arm on the space station to move perfectly in the bizarre, weightless environment of microgravity. And all of this leads to the amazing robots we see emerging today. For a humanoid robot, dynamics is the difference between walking confidently and just falling on its face. For a drone, it's the constant, lightning-fast calculation that adjusts the propellers to keep it hovering perfectly still even when the wind kicks up. You know, this quote just nails it. Dynamics isn't just one part of robotics. It's a cornerstone. It's the essential bridge that connects the idea on a computer screen to a real machine that can physically, seamlessly interact with the world around it. And that leaves us with one last big question to think about. As our robots get smarter, faster, and stronger, what's the next great physical hurdle they're going to have to clear? Will it be running through a chaotic forest, or maybe interacting with us in ways we can't even imagine yet? Whatever that next challenge is, you can be sure of one thing: robot dynamics will be the key to solving it.